Okay, so in the previous session, we were talking something about deep learning and how it consists of more layers than what we have in the neural network. So, one type of deep learning is what is called the convolution neural network. So, in the convolution neural network, you have what are called convolutions, and these convolutions help to actually capture the correct features as you go on, the what you call the higher level features. So at the beginning you'll have the lower level features, and as you go on you'll get the higher level features. So let us see what this convolution actually is. So here if your input is like this, we have what is called a filter. So a filter will be like a 3 by 3 or a 4 by 4 filter, which is moved along the input like a moving window, and whenever it is placed on the input, you take the dot product of this filter and the input, and you keep moving the filter to the right, and when you come to the end you move the filter down, and so you are going to scan the entire input in this way. So here you can see an example of a window where this is placed. So this would have started right from the top, and then it would have moved to the right, and it keeps going down till it comes to the bottom. So okay, so suppose we have a 6 by 6 image. So this is your input, and this is what you call the filter. So you're going to take this filter and you're going to place it here, that is the 3 by 3. And you will not have just one filter, you could have more than one filter. You can have a number of filters which are available, and for each filter you are going to get an output. So depending on the number of filters, the dimension of your output is going to change. So we can say that these filter parameters are what you need to actually learn. So each filter here is 3 by 3, so it detects one 3 by 3 pattern, okay, by taking the dot product of the two. So suppose we take the first filter, okay, so this is a filter, and if we place it on this input, okay, then you need to take the dot product of this and this. So when you take the dot product, what happens? You are going to get 3, because all the others here are 0. Okay, so you are going to get 3 as your output. So it is like saying you are taking the dot product of, so you are taking the dot product of 1 0 0 0 1 0 0 0 1 and 1 minus 1 minus 1 minus 1 1 minus 1 minus 1 minus 1 1. So what you are going to do actually, it's like saying you are taking 1 into 1 plus 0 into minus 1, etc. Okay, for the entire image. So what you are going to get here is you'll get 3, right? And similarly, as you move this to the right, so if this is 6 by 6, you are going to get a 4 by 4 image over here. So you then move it so to the right, right? If you move it one place to the right, it is known as having a stride of 1, okay? And you are going to get values like this, right? Okay, then so in this way you are going to get a 4 by 4 image, right? And then you take filter 2. So filter 2 again you do the same thing. So you are going to get a different values with filter 2, right? Repeat this for every filter. So you'll get these values. So you are going to get a two-dimensional image as the output. Okay. So because so if you have say 10 filters, it's going to be 10 dimensional. You are going to get 10 separate matrices in this way. Okay. So so this is what is known as your feature map. So you'll get 4 into 4 images. So you can say 2 into 4 into 4. So that's the dimension of the image that you are going to get. Now if you have RGB, okay, 3 channels, then for each of them you do the same thing for every filter, right? So you are going to get separately for each of the RGB for filter 1 and then for filter 2. So for filter 1 you are going to get like this, and for filter 2 you are going to get RGB. So 3 outputs. So this is what is known as the convolution. So you have the images and you have the filters and you get an output, okay, which is known as your feature map. And then you have finally the fully connected layer, just like you have in a neural network. So what is done is, if your image, if your matrix is like this is going to be flattened out. Okay, so it's going to be flattened, made into one dimensional vector over here, and then you have the next layer just like you have in a neural network, and all the nodes in this layer are connected to all the nodes in the next layer. So this is known as the fully connected layer. So that's the difference between what is a convolution and a fully connected layer. So once you do the convolution, you do what is known as a pooling. So pooling basically reduces the size of the convoluted image which you are going to get. You are reducing that size by taking a window, and each window is being replaced by just one value. For example, if we take a 3 by 3 window here, okay, so we are replacing this window, we are replacing the first 3 values here, this window, by just one value, okay, like this. Okay, and you do that for every dimension that you have. So there are 2 types of pooling. One is what is called the max pooling, and the other one is average pooling. Okay, so let's see what these 2 are basically. Okay, so you are going to get a new image which is smaller. Okay. So let's look at the pooling. Okay, so pooling basically, you are taking a window of this size and you are replacing these 4 values by just one value. So in max pooling, you are taking the maximum of the 4 values. So here you are going to get 20, 30, 112 and 37 like this. But if you take the average pooling, you take the average of the 4 values. Okay. So this is your average pooling which we get over here. Okay. So what you are getting finally is like this. Suppose this is what you have to recognize. You are going to have a number of convolution and pooling layers. So you will have convolution pooling, etc. And then you have the output of this pooling, which is then flattened. And after flattening, it's passed through a fully connected feed-forward network. Okay, we've seen how the neural network works for classification. So then it is used for classifying the output. So this is how the CNN actually works, or the convolution neural network. Okay. So how is the flattening done? So suppose we have this is what needs to be flattened. You take these 4 values and flatten them, and take those 4 values, flatten them, and the whole thing together will form one vector. So this is how the flattening is actually done. Okay. And after flattening, you are passing it through the fully connected layer. Okay, so the simplest architectures in CNN is what is called the LearnNet 5. So this is done by these people who's given over here, and they have given the name LearnNet 5. So 5 actually tells you the number of layers that we have. Okay, so it is the number of convolution layers plus the number of fully connected layers. So number of convolution layers plus number of FC layers. So here we have 2 and here we have 3. So it gives a total of 5. That's why it is called LearnNet 5. Okay. And average pooling is used here. So in the earlier architectures in CNN, average pooling was used. But if you look at the later architectures, you find that the average pooling has been replaced by max pooling. Okay. So it has 60,000 parameters basically around. Okay, so it has quite a lot of parameters which need to be trained, right? So what you're doing here is you're stacking convolutions, okay, which have activation functions. So you have the tan H is the activation function used here, and for the fully connected layers, the final one you're using softmax because that is needs to be used for classification. So I think I have gone through the activation functions before. So when we say tan H, the whatever input you are giving to that activation function, it changes it into -1 and +1. So that is the tan H. And in the case of softmax, every input that you are getting to the softmax is converted into a probability. So you'll find that all the values sum up to 1. So you can choose the one which gives the maximum probability and say that is the output you are getting, or that's the class label. Okay. So that's what we mean by softmax over here. So if we look at the MINIST data set, so MINIST data set is a image data set. So there the input that is being given is 28 into 28 into 1, right? So you have a 28 by 28 image, 28 pixels by 28 pixels, and then it's passed through a convolution of 5 into 5. So you have filters of size 5 into 5 and you have 32 such filters, right? And you have a padding of 2. So when you have a padding on each side, you are putting a row of 0 at the beginning, row of 0 on all 4 sides. So you find that the output of this will have the same dimension as this. So you'll get 28 into 28, but you're using 32 filters. So you're going to get 28 into 28 into 32. After that, you're using max pooling. So if you're using 2 by 2, then this will become 14 by 14. Okay, so 2 by 2 is being replaced by one value. So you'll get 14 into 14 into 32. Then again you're using padding 2, 5 into 5, but 64 filters, right? So you'll get 14 into 14 into 64. Then again you're using the pooling, so you're reducing the size of this, so you're getting 7 into 7 into 64 because you have 64 filters here. So this one is actually flattened. Okay, so after you flatten it, you use a dropout rate. So by dropout rate, it means that out of all the values which you have in the flattened one, you are going to remove some of them, okay, randomly. So you are using a dropout rate, and then you are going to get 1024 as the size of your vector. Okay. And finally, you get the output, which is 1 into 1 into 10, which means you have 10 classes, right? So that is the output that you're getting over here. So this is the same thing, okay, put out again, right? So what is being used is a stride of 1, obviously. If you don't use padding, then you find that when you do convolutions, the size of the image is going to reduce. So actually the output can be calculated by using this equation over here. Okay. So where S is the stride and P is the padding and NC is the number of channels, okay, that is the number of filters that you are using, right? So let us see how this actually works in this case, okay. So you have n as 32 because you have 32 by 32, right? Plus 2p. So suppose you are not using any padding, right? So you will get padding is 0 and f is the it is actually 5, okay, that's the size of your filter, 5 into 5, okay, divided by stride is 1 plus 1, right? So you are going to get 28. So you are getting 28 into 28 into 6. So NC is the number of channels, which is the number of filters. So you are getting 28 into 28 into 6, right? So this is how this actually works. So next we have the AlexNet. So what they do is that as time goes on, they just sort of increase the number of layers that you have. So, okay, so they increase the number of convolution layers. Okay, so we had 3 convolutions there. So here they are using 5 convolutions. Okay, so you have 1, 2, and 3, 4, 5. Okay, so you have 5 convolution layers and 3 fully connected layers. So you get altogether 8 layers here. Okay, and when this was actually brought out, it was one of the largest CNNs at that time. Of course, after that they have actually gone much beyond that. Okay, so what is supposed to be the novelty of this? First use of ReLU. Okay, so you use the ReLU activation function and the softmax activation function. So what does the ReLU activation function do? If the value of the input to the activation function is below 0, that is negative, it puts it as 0, and if it is positive, it reflects the same positive value as your output. So that's the ReLU activation function. Okay, so we can see that they are talking about 224 and 224 into 3 input. Then you have the convolution, which consists of 11 into 11, the filter size. Then max pooling is 3 into 3. Then you are using convolution of 5 into 5, etc. Right? So here it gives you the complete details. Okay, so if we have 227 here into 227, and you are using filter of 11 into 11, okay, and a stride of 4 is used, etc. So you can calculate what will be the size of your the output of this. So you are getting 54 into 54, and you are using 96 filters, so you are going to get 96 there, and then you are using the max pooling 3 into 3, okay, with a stride of 2. So if you calculate, you will get 27 into 27 into 96. And then again you use convolution 5 into 5, okay, with a padding of 2. Okay, so since you are using padding of 2, this remains as 27 into 27, but you are using 256 kernels, so this dimension increases, right? So what is happening is you are reducing the size of the image as you go on, okay, till finally you are getting 6 by 6 as the image into 256, okay, which is then flattened and passed through these things. So you are going to get like 4096 as the number of neurons in this vector, and then you are using fully connected layers to get the output. So this is what is called the AlexNet. So we can see input layer, convolution plus pooling, convolution plus pooling, convolution, convolution, convolution plus pooling, and then you have the fully connected layers. So this is used on the ImageNet data set. Okay, so this gives you the same thing in more detail. Then we come to what is called the VGG, which was done by a group called Visual Geometry Group. So they called it VGG, right? So VGG 16 means it has 16 layers basically. So here we have two convolution layers here into 2, so that is 4. And here we have 3 convolution layers, that is 9. So 9 plus 4, 13. So we have 13 convolutions and we have 3 fully connected layers, making it altogether 16. Okay, so this is VGG. So they are just going deeper and deeper, right? So you find that you have 138 million parameters and takes up about 500 MB of storage space. So you find that the parameters are just going up. Okay, so it's a deeper, and you have even more deeper variant, which is VGG 19. Okay, so what you're doing is you're stacking more layers and making it deeper basically. Okay, so this is the VGG 16. Okay, so we have, starting from here, the convolution layers, 2 convolution layers, a pooling, and then again pooling, etc. Okay, so you're using 3 convolution layers, then pooling, and finally you have the fully connected layers. So it's just an extension of your LearnNet, okay, making it deeper basically. So you can see the comparison of AlexNet and VGG. So VGG is definitely much deeper than the AlexNet, and AlexNet is deeper than the LearnNet which we saw. This is a Google Net, which actually is much deeper and has a lot of parameters, etc. Okay, so we'll not go into that. So the next type of CNN you have what is called the Inception or version 1. Okay, so here what you are doing is that you are using the inception blocks. Okay, so first you use what is called the stem. So here it's just you have a convolution layer, max pooling layer, convolution layer and max pooling layer. Okay, once you do that, you are using the inception blocks. So this is the inception block. So you can see that it's fed parallelly into a number of convolution and max pooling layers. And once this operation is done, it's again concatenated and given as the output. So these are used, instead of using the convolution blocks we saw earlier, you use the inception blocks. So this inception module is like a network by itself. Okay, so it is known as a network in network approach basically. And there you can see they are using max pooling. So there's also average pooling and max pooling, both are being used in this architecture, right? So this was around 215 basically. Okay, so this is a 22 layer architecture with 5 million parameters, network in network approach. Okay, so these are the ideas which have been used here basically. One is that you have a parallel tower of convolutions with different filters. Okay, so you have filters like 1 into 1, 3 into 3 and 5 into 5. Okay, the 1 into 1 convolutions are used for dimensionality reduction, and since you are using activation functions there, it also adds some non-linearity to the whole thing. Okay, and you have 2 auxiliary classifiers. Okay, so the auxiliary classifiers are, so that discrimination is done even at this level, even before reaching the final level, and that can also be used for updating the weights of your network. But finally, when the network is trained, you're going to remove these auxiliary networks basically. So what is the novelty in this? Using the inception blocks and okay, stacking modules blocks used where convolutions are inside the blocks. So this is the what is called the network in network approach. Then you have the inception version 3 where you have 3 different inception blocks. Okay, you're not using only one type of inception blocks, but you have 3 different types of inception blocks which are used over here, and you also have classification being carried out in another block over there, right? So let's see what is the novelty here. It used what is called batch normalization. So what is batch normalization? A batch um, at a particular level, okay, at this particular, before the input is given here, the input is normalized. Okay, so how do you normalize the input? It is, for example, you may find that the input is, varying a lot. You may find values which are very high, you may find values which are very low, etc. So you bring them down to values, say between 0 and 1. Okay, one simple way of carrying out normalization is find the largest value and divide everything by the largest value. So what happens is you'll get values between 0 and 1. Okay, there are some variations of doing this batch normalization. You can find the mean and the deviation, okay, the standard deviation, and you can use that to normalize the values basically. Okay. Then we have ResNet. So ResNet, what you're using in ResNet is basically, it's just a deepening of just like LearnNet, it goes more into deepening the network. But it uses what is called the skip connections. So what happens is the input which is got from, say, from here is used somewhere later on in the network. That's what we mean by skip connections. So what are the novelty here? It uses skip connections. It designs even deeper networks. And among the first to use batch normalization. Even the previous method was using batch normalization. So here we can see that now the max pooling is used rather than the average pooling. Okay. So that's the thing over here. Okay, so we can see this is the full ResNet that we have over here. Okay. So you are using 7x7 convolutions. Then you are using different types of convolutions here, okay, which are combined together, etc. Okay, finally you have the fully connected layer down at the bottom. Then you have the exception, which is something like you have different convolutions, convolution A, B, and C, and it's called separable convolutions basically. Okay, so it's a sort of a variation of the same things. Okay, so this has 43 million parameters. So what is the change from the inception version? It adds more inception blocks, etc. Right? So we can see they're just making it more and more complicated basically. Okay. And this one is inception ResNet. So you're using the combination of inception as well as ResNet. Okay, so you have you're using inception A, inception ResNet, which consists of inception, that is parallel blocks, plus making it deeper basically. Okay, inception ResNet B, inception ResNet C, etc. Okay, so these are some variations that we are using over here. Okay, Res next 50 is another variation. Okay, so here also you are using the convolution blocks basically. Okay, and the identity blocks. Okay, then we come to the dense net. So in the dense net, basically it has a lot of skip connections. Okay, so if we take one block like this, a dense block, you find there are a lot of skip connections here. Okay, and then it goes through what is called the transition layer. Okay, where you have some convolutions done plus the average pooling, and then you get the dense block 2 where again you have a lot of skip connections over here. Okay, so so these skip connections in a block. Okay, so that is the speciality of this dense net. Okay, so you find that these are all the applications of using DenseNet. It was first used for image classification, then it's also used for segmentation and other medical imaging, etc. Right? Okay, so bit transfer is a scalable ResNet based model. Okay. So we can see that we saw a lot of CNN architecture. So they have been just listed over here. We started with the LearnNet and then the AlexNet, VGG, Inception, version 1, 3, ResNet, Exception, ResNet, DenseNet. Then finally you have what is called the Efficient Net. So what we can see here is that if we look at all the CNN models that we spoke of, okay, and we look at the accuracies, we can see that efficient net is doing fairly well, and what is called meta pseudo labels is also doing well. Okay, so these are the more recent uh, architectures. So we started off with the here we are talking about the AlexNet, and we can see the number of parameters that are there. Okay, so we can see that as you go down, mostly the number of parameters are going up, but we can see that DenseNet has only 8 million parameters and has 75% accuracy as compared to say Inception, etc. Okay, but these have a lot of, like VGG has a lot of parameters. Okay, so we can actually say that just increasing the number of parameters doesn't always give you a better result. Okay, so we can see that the DenseNet model is more compact. Okay, because you are not having so many layers, right? But you're using what are called a lot of skip connections over there. Okay, and it's giving fairly good result. Okay, so these are the standard results that we can see here. Okay, again, if we look at the results on various CNN models, we can see this gives the top 1 and the top 5 accuracies. We can see that the best is this Inception ResNet version 2, right? And it doesn't have, of course, it has a lot of parameters, but not as much as the VGG. Okay, but it is doing a lot better than the VGG, we can see. Okay, and the others have parameters which are fairly medium, right? Not that many parameters, and doing fairly well, right? Okay, so that is about the CNN architecture. So now the CNN architecture may not be suitable for all types of problems. Okay, so we have what is called the RNN. Okay, so what is the principle in the RNN? So the output of the previous layer is fed as input to the next step. Okay, so in this way, what you can do is, depending on how long your input is, you can change the size of your RNN architecture. Okay, that becomes difficult in the case of the CNN. Okay, because the input in the case of RNN could be like a sequence, okay, and you don't know what the length of the sequence is going to be. For example, here the input to your RNN is a sentence, okay. So it says it was an awesome movie. And what will be the output? The output will give you the part of speech of each of the words that you have, right? So for this, the CNN may not be suitable because you don't know what is the length of the sentence, and whenever you have a different length of sentence, you'll have to change the size of your CNN architecture, etc., which is very cumbersome, right? So what is used here is the RNN. So in the RNN, you have these layers here, okay, which are which has an input, okay, which is the input which you are giving in, right? And then you have the U, which is the weight over here, and you can say that every layer has um, a representation from the previous point. Okay, so here you have SI coming out, which goes in as input to the next um, uh, next input. Okay, so here we have the second input coming in, and you have the input from the previous layer. Okay, and what you are getting there is you will get an output, and you will also get a input to the next layer. Okay, so here SI is the input which you are giving to the next layer, which is a function of U into Xi. So this is the weight here, U into Xi, plus W into Si minus 1. So you have, so if we consider this layer, okay, this output here, that is Si, will be equal to U times this input which you are giving in, W into Si minus 1, which comes from the previous layer, to give the next layer. And Yi is your output, which is a function of V, that's the weight here, into Si plus C. Okay, so it depends on basically on Si and the weight V, which is being updated every time. Okay, so this is how the RNN actually works. Okay, so we can see that every value here has an input. So what we called Si there. Okay, so you have H naught coming into it, and you have the input here, and you have the output which is coming out there, and you have H1 which goes into the next layer. Okay, so the simplicity here is that you have just one function f. Okay, so f is it's not different for each of these layers. Okay, you just have one function f which you are going to use here. So this is the RNN, and we can say that the RNN is used for a number of types of problems. For example, say sentiment analysis. So what you are doing is you are giving as input, say, one sentence, okay, or maybe a few sentences, a document, and the output is the sentiment of that. Okay, so the sentiment could be either positive or negative, or it could be positive, neutral, negative, or you could have more number of sentiments which is being expressed with that. So if you consider the output is just one. Okay, so you will have a number of you will have a number of inputs x1, x2, x3, etc. But there will be just one output at the end of that. Okay, it will be, we will see that little later. And in the case of say summarization, what you find is you will have an input which consists of a document. Okay, so that is a number of sentences, right? And your output is going to be another document, okay, which actually summarizes that. Okay, so you are going to give the input, and that is going to be summarized, and the output is got from that. Okay, so this way these are some of the applications for which RNN is used. So in the case of say sentiment analysis, it's like many to one. Okay, so the input is many, output is just one. Okay, in the case of summarization, you have many inputs and you have many outputs. So it's called a many to many network. Okay, you could also have one input and many output. For example, suppose you want to you have a image and you want to get a caption for that image. So what you do is you are giving in just one input, which is the image. Okay, and the output you are getting is a output of which consists of a number of words, right? So you can say that that is one to many. Okay, your input is one, but your output is many. Okay, so these are some of the applications of RNN. Okay, so we'll stop at this point, and in the next session, we'll talk about how different types of RNNs. Okay, how you could have deep RNNs or two-dimensional RNNs, etc., and some applications which you can do with RNNs. So we'll stop this session at this point.